So if anyone has said, hey, you're a pretty attractive person, they're probably talking about gravitation, right? Because any two objects that have mass are attracted by a gravitational force. Now it's really small here on Earth, but it gets much bigger when you get more massive objects, like looking at the gravitational force between the Earth and us. It is attractive, which means that it is a force that carries one object towards another object. So if we look at the Earth and the Moon, for example, they both have forces that are equal and opposite. According to Newton's third law, forces always come in pairs that are equal and opposite. So they both have equal and opposite forces on them. The difference is that the Moon has less mass, so it has a bigger acceleration than the Earth does, but the force is equal and opposite. Now, we've simplified here on Earth to find the gravitational force known as the weight using this. On Earth, F sub g equals mg, right? Where g is 9.8 meters per second squared. If you go to other planets, you can use that same equation, but g might be a different value. It might be 3 meters per second squared on a place like Mars. I think Mars is about 4 meters per second squared. On Earth, it's 9.8. However, you can look at gravitational forces anywhere. And this really is just a simplified version of this equation here. F sub g is the force of gravity. And we see that the force of gravity depends on a few different objects, a few different variables. G, this is a big G. This is different than the little g here. This big G, which you're really only going to use for this equation, is the first thing you'll see on the reference table, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. You probably won't remember that. You don't need to. It's on the reference table. Mass 1 and mass 2, those are the masses of the two different objects. And r is the distance between them in meters. So if you want to find the gravitational force between two objects, you just need to know the mass of each of those objects and the distance between the two objects, plus this constant here. It turns out, if you look on the surface of the Earth, you can say, oh, this is me on planet Earth. If you use your mass, m, and the mass of the Earth, and you use r as the distance between you and the center of the Earth, which is actually the radius of the Earth, is the distance between the center of the Earth and you, pretty much the radius of the Earth. And you put them into this equation, it simplifies out into g times the mass of the Earth divided by the radius of the Earth squared simplifies out to 9.8. That's where we get 9.8 meters per second squared. But this is the more robust equation that we will need to use at times. G m1 m2 over r squared. Now, a couple things to keep in mind. This is an inverse square law, meaning a small radius, or small distance, I should say, I'm just going to say small r, meaning you are very close to another object, gives you a big force. A big radius gives you a small force. So that tells you it's inverse, and it goes with the square of it. So it goes with r squared. So if you double the distance between two objects, that means r is doubled. If the radius increases, then the force has got to go down, but it's not going to decrease just by a factor of 2. Force decreases with r squared, so it becomes 1/2 squared, or 1/4 as big. If you have the distance, meaning you get twice as close, the force is 4 times larger. If you get 3 times as close, the force is 9 times larger. That's what you get with an inverse square law. And if you were to graph it in terms of force in distance, the graph would look something like this. The larger the distance, or the larger the r, either way, the smaller the force. The smaller the r, the larger the force becomes. Thank you very much for watching.